Welcome to the lecture on computer aided design and manufacturing. See, these computers played a major role in bringing all the informations to digital form. Today we don't call it as CAD or CAM, we call it as digital manufacturing. This digital gave a big boon to the manufacturing. One, in terms of creating objects whatever we want. Two, the created objects could be manufactured just by transferring the digital data from CAD to manufacturing environment. Let it be rapid prototyping, let it be rapid manufacturing, let it be measurement, let it be machining. So, all these places a single data could be exported, imported, and people could use it for producing their required output. So, computer played a very major role. I would reframe, the digital technology played a very major role. So, the data could be stored, the data could be retrieved, the data could be easily edited too. And once you start doing this and you have it at a common place, then all other people, when they retrieve, when they use that data, they take it from this database. So, this database in the digital form became a center core where everybody used the center core for their application, and then they could edit, correct, save, store, latest version change, everything they could do at their end, and the data could be transferred. So, computer played a very important role. When we talk about engineers language is drawing, so initially these computer there were softwares developed for drafting, and later came the additional knowledge which we started doing on analysis and optimization. So, today it has become computer aided design, and the same data could be used for manufacturing. So, computer aided design and manufacturing will be this lecture. We will try to study more. The rapid manufacturing, whatever we are talking in this course, could happen only because there was a provision for taking reverse engineering data, or there was a provision for starting the data forward direction from CAD files. So, this made a big change. So, in this lecture we will see some introduction, followed by introduction we will try to see geometric modeling. So, if I know to draw a line and if I know to draw a curve digitally, then that solves all the matter. So, if whatever complex objects I have, if I could discretize into lines and curves, then I am in the business. So, geometric modeling could be done, then followed by it we have Bezier curves. So, first we will see how to draw lines and then we will see how to draw curves. So, Bezier curve, B-spline, then we have constraint based modeling, we will see wireframe modeling, then types of solid model, constructive solid geometry, feature recognition and design, then feature recognition design, wherein which we saw feature based design and feature interaction. So, these are the contents which we will try to cover in this lecture on CAD and CAM. CAD and CAM are nothing but computer aided design and computer aided manufacturing. It is the technology concerned with the use of computers to perform design and manufacturing function. So, this design, when we said, as I said earlier also, it will involve drafting. On top of drafting you will have analysis, simulation and optimization. This we will do in this designing. Okay. So, all these things could happen, softwares could talk, everything could happen because the data was in digital form. It can be in ASCII, it can be in binary. If you want to read, if I want to read, it will be in ASCII. If machine has to read, it will be predominantly binary. Okay. So, manufacturing function and manufacturing function. The CAD can be defined as a use of computer system to perform certain functions in the design process. CAM is the use of computer system to plan, manage and control the operations of manufacturing plant through either direct or indirect computer interface with the plant's production resources. This is CAM. For CAM definition, the application of CAM falls in two broad categories. One is computer monitoring and controlling, and the other one is manufacturing support application. Computer process data, you have a process. Computer process data and control signals, this is the advancement. So, first is computer process, the processing data is flowing. Computer process data and control signals are there. So, computer monitoring and control and manufacturing support application. So, in manufacturing support application, you will have computers and manufacturing operations. So, process data and signals will flow here. So, this is manufacturing operations. So, the CAM is divided into two categories: computer monitoring and control, manufacturing support applications. When we talk about manufacturing support applications, it talks about supply chain and other things. Supply chain, HR, logistics. When we talk about computer monitoring and control, it talks about machine and sensors for online monitoring. The product life cycle and CAD and CAM. In order to establish the scope and the definition of CAD-CAM in an engineering environment and identifying existence and future related tools, a study of a typical product cycle is necessary. We will see the product cycle in the next graph. The following figure, the next shows the flow chart of such a cycle. The product begins with a need which is identified based on the customer and market demand. So, this is the graph or the schematic representation of the complete setup. So, here you can see there are two parts, one is design part, the other one is manufacturing part, and here you can see here CAD process and then you have synthesis here. So, this is analysis. So, the CAD process, in CAD process what do we have is, we will have designer need and then design specification, definition, specification and requirements, and then collection of relevant design informations and feasible studies. Okay. After this comes the design conceptualization, then design conceptualization to design modeling and simulation. This leads to design analysis, design optimization, design evaluation and design documentation. So, you can see this, these are all part of the design process. Customer need, from the customer need you put a spec, from after putting the spec you do the state of the art, after doing the state of the art you develop concepts. These concepts are all proof of concepts, and you can have functional requirements added to it. Then what you do is you try to optimize the developed POC such that it can go to the market. Once you try to do that, you will also try to have analysis, optimization, evaluation. So, here it is only modeling and simulation. Once you simulate, then you optimize. When it comes to the manufacturing point of view, so the data from the documentation goes to process plan. In the process plan, it is divided into four. One is production process, design and procurement, order material, and NC, CNC, DNC. DNC is distributed numerical control, wherein which you have a main server and you have several CNC machines attached to the server. Every time the information is pulled out from the server and then it is executed in the CNC machines. And here if you have a long program, it is done, and if it goes line by line or segment by segment, if it goes, then it is called as drip numerical control. Okay. So, but what here we are talking about is direct numerical control. Then all these things put together in a capsule comes towards production. Once you produce, you have to check for the quality. After you check for the quality, you say yes, it gets into packaging. Moment it gets into packaging, it gets into shipping. Shipping, it goes to the market, and then you try to complete the entire cycle. This is the complete product life cycle for CAD and CAM. The product goes through two main processes from the idea conceptualization to the finished product: design process, manufacturing process. The main sub process that constitute the design process are synthesizing and analyzing. Synthesizing is you have umpteen number of data, so this data has to be genuinely looked into and you remove the noise, you then consolidate the data into an information, that is synthesizing. Synthesizing of a design is a very tedious process. Once you synthesize, then whatever you get, you start analyzing what you did in the synthesis. So these two are the subgroups. If you go to the previous figure, you can see synthesizing cycle. Synthesizing means this all process is you have collected data and then you convert the data into information and then into knowledge. The implementation of a typical CAD process on a CAD/CAM system, it involves delineation of geometric model, then you define translators, then you try to go for a geometric model, then you have an interface algorithm. So here this interface algorithm goes to design and analysis algorithm. So here design changes can happen between these two, then comes drafting and detailing, documentation, and finally a CAM process. When we try to implementation of a typical CAD process on a CAD/CAM system, these are the steps which are involved. So the CAD tool required to support the designing process, these are the tools. At design conceptualization, we need a geometric modeling technique, a graphic aid, manipulation and visualization. These are the requirements for the CAD tool. When design modeling and simulation has to be done, same as above, you will have animation, more assembly and special modeling packages. Design analysis package, customized program and packages. Design optimization, customized application and structural optimization can be done. These are the requirement of the CAD tools. Design evaluation for dimension and tolerance. So there is a big scope in dimensioning and tolerancing. Okay. And bill of materials and numerical control. Design communication and documentation will be drafting and detailing will be there. So these are the design phase and these are the tools which are involved in the design phase, or these are the tools required for CAD implementation. When we have to implement a CAM process is whatever you have developed in the CAD, you do a feature recognition, each feature has a process attached to it, then these processes are chosen, the machine is activated. So the machine knows what it has to do, like what process parameter, what is the tool path, and then it executes along with it to get an output is the CAM process. So geometric modeling, interface algorithm, process planning is done, NC programs are generated, then you inspect, assemble, package and ship. So these are the implementation of typical CAM process on a CAD/CAM system. In the same tool, what we saw in CAD, if you want to do a CAM tool requirement to support the design process, manufacturing phase will be planning, process planning, part programming, inspection and assembly. So in process planning, we have computer aided process planning. So computer recognizes the feature, generates a process plan and tells you. Costing analysis, which can be taken from CAP, material and tool specifications. These are all part of process plan. Then part programming, numerical programming is done, inspection, computer aided quality control and inspection softwares. Assembly, robotic simulation and programming are some of the CAM tools which are used for CAM environment. So if you look at it, computer, graphic and concept, geometric modeling is a separate circle and design tool is a separate circle. This can happen independent. This is just which a computer alone, this is the model alone and this is the design alone. So if you see, CAD tool is a combination of A intersection B intersection C. Okay. It takes a common zone of the three things in the CAD tool. So takes a position here. So in the CAD tool, that means to say you will have computer graphic concept, you will have geometric model, you will have design tools. When we talk about a CAM tool based on constituent, networking concept, CAD and manufacturing, all these things meet at a point that is called as a CAM tool. All the CAM tools fall here. So you should have networking concepts between two machines. Today we have wireless, wired. So networking, then you should have CAD and the machine tool. Machine tool or manufacturing tool is the machine basically we are talking about. So when we talk about CAD/CAM tool based on their constituents, It is design tool, manufacturing tool, networking, computer graphics, geometry, all of them meet at a point which calls as CAD, CAM and tools. CAD standards. Need for CAD data standardization is very important, so that this CAD data whatever gets developed can be transferred to another system in a unified manner. So, there is a need for CAD data standardization, understanding the graphic kernel system and its extension for developing the graphic software systems. So, you should know what is the minimum hardware required to run the software. Requirements of graphic data exchange format and their details in IGES, DXF and STEP. These things are called as neutral files. What are neutral files? You have a system, you have a software, you have another software or a machine. So, in this, if you want to transfer the data to this machine without any seamlessly, without any interference, so then this is called as a neutral file. So, these are some of the standardization in the graphics. GKS, graphical kernel system. You also have IGES, initial graphic exchange specification, DXF, drawing exchange format, standard STEP, standard for the exchange of product model data, and we have VDI, virtual device interface, VDM, virtual device meta file, and MAPLAPS, North American presentation level protocol syntax. So, all these things are standard neutral files which are used to transfer a graphic data into a manufacturing data. So, when you draw a component, after finishing the component you can store the extension as star.dxf. So, now this becomes a neutral file such that when you move from one software A to software B to process the data, then you need a neutral file. So, all these things are part of neutral file. Various standards in graphic programming. So, you have graphic database wherein which you use these neutral files DXF, IGES, STEP and SET. Then we have application programs wherein with GKS, PHIGS and then core you have. You have graphic functions which are VDI, VDM and MAPLAPS. So, then this will be further divided into device driver. You can have two different devices which will all get linked to get the graphical program. GKS, which is graphical kernel system. The main objective that were put forward for GKS are to provide a complete range of graphical facilities in 2D, including the interactive capability. You can edit, move and do. To control all types of graphic devices such as plotter and display devices in a consistent manner. So, this was the requirement for GKS. GKS again is a transfer of data from a CAD system to the device to be small enough for a variety of programs. So, these are the requirements which was put so that the data can be transferred from a CAD file from a CAD system to a plotter or to another accessory or to a machine. The layer model of graphic kernel system is you have application programming, then application oriented layer, then language independent layer, then graphic kernel system. You have an operating system which is at the base. In the operating system again you have two other resources and graphical resources. So, these two are added to the operating system, then graphic kernel system, language independent layer, application oriented layer and application program. Graphic primitives in IBM GKS are bar, arc, pie slice and circle. These are all primitives which are already available in the graphic kernel system. Other graphic standards are GKS 3D, PHIGS and NAPLS. So, the data exchange between various systems is CAD A to CAD B, CAD B to CAD C, CAD C to CAD D. So, you can have A B, B C, C D, D A. So, you can see all these things are linked. So, the data exchange between the various systems is very important. Otherwise, In manufacturing, what will happen is you will have islands of automation, but all these automations cannot talk to each other. If it cannot talk to each other, then there is a big difficulty. Every time the data has to be transferred into the other system manually, and then you start doing some editing process. So, development in the drawing data exchange format, these are the years when it was started, and here are the contributions made, and this is how the evolution happened. So, IGES 1.0 came, then ANSY SI Y14.26M came, IGES 2 protocol, IGES 3 protocol, 4 protocol, 5.3 protocol, which came in new, it is 1996, and this led to ISO step. And in between, if you see, IGES 3.0 led to a PDES, which is nothing but product database format, PDES, and PDDI, they all came into existence. So, here if you talk about, it is shape based format, drawing, initial shape based format, then it is product database format, and then finally from all these evolution, today we talk about step, which is used, wherein which the process details are also attached with the feature whatever is getting generated. IGES is the most comprehensive standard and is designed to transmit the entire product definition, including that of a manufacturing and any other associated information. So, IGES, again a neutral file, DXF, IGES, GKS, all are neutral files. CAD system, CAD database, neutral file format, you need a pre-processor, you need a post-processor. First, what all has to be changed, it is pre-processed. Once the process data is done, then again it has to be post-processed to get the requirements. So, for every CAD system you will have the same. This is CAD B, you had a CAD database, you had a neutral data format pre-processor. So, this gets into the post-processor. Then the neutral data format of the this is there. So, this in turn will be linked to the CAD database. Okay. So, the data transfer from A to B is there. So, it happens from A to B, or the data transfer happens from B to A. The only difference is, if you say B to A, neutral data format pre-processed gets into the post-processor, so that the data is understood by the other CAD system in a very logical manner. So, this is how an IGES file looks like. A component which is a bolt, okay, with a threading, with a head, component drawing, and a part of IGES file generated, you will see a stack of data, a column of data, wherein which it talks about an arc, line, B-spline, and then you have a curve, you have other surfaces. So, this is how the output looks like of IGES, which is pre-processed, post-processed, such that the other system can understand. The latest standard which we saw, ISO STEP. STEP is nothing but standard for the exchange of product model data. So, today we are not trying to transfer the data from one CAD system to the other as individual features or individual entities, but we are trying to completely shift it like a product itself. Like writing a small library function, a library function is already written. In this library function, all the time you just put some parameters and you change the requirements whatever you want. For example, you have a library function of making a bolt. So, then all you have to say is what is the pitch you need, what is the length you need, what is the head you need, all those things. So, then the system itself generates. Okay. So, a step, what will happen is you will have other details like manufacturing tolerancing, and other details will also be attached along with the entity details. A broad scope of step is as follows: the standard method of representing the information necessary to completely define a product throughout its entire life, that is, from the product conception to the end of the life, can be done by step. The standard method of exchanging of data electronically between two different systems is done using the step. The step application protocol AP203 explicit for drafting. So, you can see here product relationship, part, responsible, organization. So, A, B, C, D, E, you look at a part, so it will get projected in different planes. So, you get B, C, A, D, E, all are projections of the same object into multiple walls or multiple faces. So, you have so many informations getting out of step. So, product realization relation, part responsible organization, then geometric shape, geometrically broadened 2D shapes, then annotation text, annotation curve, symbol, subfigure, filling area, dimensions, then we have grouping of them, then we have drawing structures, drawing revision, sheet revision, view, drafting specification, contract, security classification, approvals and responsible organization. When we talk about controlled design, AP 207 come into existence, you will have configuration management, shape. So, here you can see advanced BREP, we will see what is BREP as and when we go down. Then we see product structure, we see simplification. Today when we talk about the softwares which are ERP softwares, wherein which product structure, bill of materials, all these things can be attached directly to the CAD file and you can extract, and then further information can be sent to different departments of the manufacturing. So, step application protocol AP 207 configuration control design is this. Here is another example for step file generation, sheet metal die planning and design. So, again shape, definition, item, and then you will have process plan, and then you will have whether the work is internal, external, start or change. DXF we saw, which is used by AutoCAD. The dimensional measurements interface specification DIMS is a new standard of communication being established by CAM1 for manufacturing. So, now initially DXF and IGEF is only to transfer the data from one CAD file to other CAD file, but one moment step came into existence, it is used to transfer a CAD data to a CAM environment, and with more, and the protocol is more and more focused towards manufacturing, wherein which dimensions, tolerances, the product life cycle, everything can be done. Okay. So, now let us move to the new topic, which is on geometric modeling. How do I draw a part in a CAD file? That is geometric modeling. So, I will try to model a part in a CAD file. Objective here to understand the various requirements for the information that is generated during the geometric modeling stage. Study various types of geometric modeling possible and their application, develop various methodologies used for geometric construction such as sweep, surface modeling and solid modeling. Recognize the various types of surfaces and their application as used in geometric modeling. Appreciates the concept of parametric modeling. Parametric modeling, which is very important, we will see later, which is the current mainstay of most of the 3D modeling systems. Develop the various mathematical representations of curve and surfaces using the geometric construction. Understand the parametric representation of curves and surfaces, and then finally understand the solid construction by including BREP and CSG. When we talk about geometric modeling, the requirement for the geometric modeling is you have to have an idea, you have to have a production, you have to have a design analysis. The center part is the geometric modeling. The geometric modeling is the center part of the product design. What are the functions of a geometric modeling? In the design analysis, it is used for evaluation of area, volume, mass, inertial properties, checking in assembly, tolerance building in assembly, analysis for kinematics, that is mechanics and robots. It is also used for auto mesh generation for finite element analysis. All these things are done at the design stage, design analysis. Then when we start using this for drafting, geometric modeling for drafting, we automatic planar cross sections we can get, automatic hidden line and surface models, automatic production of shaded images, automatic dimensions and automatic creation of exploded view for the technical illustration. All these things are functions of a geometric model. Here it is more of drafting. So, that is only drawing. So, that is why you see cross section, you see creation of exploded views and all those things. Here if you see area, volume, CG, mass, all these things can be evaluated from the design analysis. When you talk from the manufacturing, the geometric model is used for part classification. What is part classification? Part classification can be done based on the design similarity or in the manufacturing similarity. Design again can be divided into prismatic and it can be divided into circular. So, they basically, if you see later we will see about group technology. If I wanted to classify the part and give a part number to it, the geometric modeling plays a very important role. That is the input data. Then process planning, numerical control data generation and verification, and robo part generation. So, these are the functions of geometric modeling in manufacturing. When we talk about production engineering, bill of materials, materials requirement, manufacturing resource requirements and scheduling, all these things are functions of geometric modeling. And finally, when we talk about inspections and quality control, the program generation for inspection machines and comparison of produced part with the design are part of inspection and quality control. Today what we talk about is use the same center data what you have created for CAD to CAM, CAM to CAQ, computer aided quality control, you check. So, now what we talk about is we talk about CAD, CAQ and all these whatever it is CAI, it is all leading towards CAE, computer aided engineering. The Volcker specified in the following properties to be desired for or desired of in any geometric modeling system. The configuration of the solid may stay invariant with regard to its location or orientation. Whatever orientation you take, whatever location you take, you view from the front view, you from the top, the geometric model should have a consistent figure. There should not be any variance. The solid model have an interior and must not have isolated parts. Must have an interior, solid must have an interior and must not have isolated part. For example, you cannot have something like this and say these two are interlinked. No, the solid must be finite and occupy only a finite space. So, if this it should be a closed volume and it should occupy a finite space. That is why if you go back and see it, you can do mass calculation, inertia calculation, volume calculations and CG calculation, all these things could be done. It must have a finite and occupy only a finite shape. The application of transformation or other operations that adds or removes part must produce another solid. So, if you have a solid like this and you have a cylinder like this, you say A minus B, you should get something like this, an object with a hole inside. Okay. A model of the solid in Euler space may contain infinite number of points. However, it must have a finite number of surfaces which can be described. All these points are very, very important to validate an object or to put it as functions of a geometric model. The boundaries of the solid must uniquely identify which part of the solid is interior and which part is exterior. All these things are very, very important for us in this course. Why? The CAD whatever you create, if it does not follow the functions of a geometric model, then this data will be transferred to the rapid prototyping machine, and the rapid prototyping machine, it will start executing. Moment it executes, if it does not identify interior and exterior, it is too difficult for it to build a part. Second thing, if it does not form a finite volume, for example, if you say that I have a square like this, this data is given to rapid prototyping, this is a CAD data. When it goes to rapid prototyping, it will try to generate a part like this, because here since it is not closed, it takes rest of everything is a valid object. It continues and makes this projection as part of the rapid prototyping process. So, geometric modeling is very, very useful. The functions of a geometric modeling is very useful, or the properties of the geometric modeling is very useful as far as rapid manufacturing is concerned. Any mistake here, when it is taken to the next stage, gets amplified. So, geometric modeling can be 2-dimensional, 3-dimensional. When we talk about 3-dimensional principal classification, they fall under line, surface and solid. So, if you look at geometric modeling, I have a dot, dot and a dot leading to a line, dot and a dot vertices to edge, right. These are edges and these are faces, and several of these faces join together to form a solid. So, point to line, line to surface, surface to solid. So, these are the three principal classifications in geometric modeling. So, you can see here P1, all these things are points, P1, P2, P3, P4, P5, 6, 7, 8, 9, 10, 11, 12. So, these are, so P1 to P12 are the points. So, these points are joined by a line. So, now these points and lines join together to form a surface. So, you had P1 to P12, now you have S1 to S8. So, S1 to S8 are surfaces, S1, S2, S3, S4, S5, S6 at the back side, S7 at the bottom and S8 at the other side. Now, this surfaces from 12 points 8, it is now converted into volume or a solid. So, you have a solid or a volume which is only 2. That means to say point line gets converted into surface, several surfaces or faces put together jointly to form a volume or a solid. So, this is line model, this is surface model and this is volume model. So, in geometric modeling you will have all the three possible things. In geometric modeling, when you represent it in a wireframe. So, what is a wireframe? Wireframe is nothing but you had points and these points are joined by a wire, and this representation tries to give for a solid. But unfortunately, when you use wireframe model, it gives lot of misinterpretations and it can also give you a solid which is not very valid. Okay. But it occupies a very less space. So, editing and storing becomes little easy, but the interpretation, representation, it is not ambiguous, or I would put it like this, it is ambiguous, the representation is ambiguous. Impossible objects can be modeled using this wireframe. So, you see here, so this is an object which is like this, you have to see like this, and here if you see the block or the beam goes behind the column. So, geometric modeling, wireframe model can be used to model impossible objects, or it leads to ambiguity. So, that is why wireframe is not exhaustively used. Generation of 3D geometry using planar surfaces, you have so many surfaces. So, these surfaces join together to form a solid. So, comparing the three different models, line model, surface model and solid model, what we want as far as rapid manufacturing, rapid prototyping is concerned is only volume model, that means to say solid model. We are least bothered about line and surfaces. Okay. Automatic view generation, impossible in line model, impossible in surface model, possible in volume model. Perspective and orthographic is possible only in volume. Cross section, if you want to do, it can manually you can guide it. So, surface also manually guided, but volume possible, even automated cross hatching is possible as far as volume is concerned. Elimination of hidden details, it is manually guided, here it may be possible, here it is pakka possible. Analysis function difficult because it is line, and then surface also it is difficult, but here it is possible. Numerical control applications difficult or impossible, here it is automatically possible, here it is automatically possible. So, what we need for RP is RM additive manufacturing is volume model. The three-dimensional geometry construction method which extends from 2D that is normally used are linear extrusion and translation or sweep. What are we trying to say is, suppose I draw a square and then I say please extrude the square along this line. Now, you get a channel. So, if I want to represent this, I can represent it as a surface, and then I say in this direction Z, please try to give a thickness of 5 millimeters or 5 meters, whatever it is. So, this is line extrusion of the square or a rectangle. Translation sweep, okay, this is also called a sweep, line extrusion or sweep. If you want to do a rotation sweep, so this object, when you have a rotational sweep, tries to convert it into a full solid object. This is rotational sweep. So, the 3-dimensional geometric construction method which extended from 2D. See, these first we did only 2D, point, line and then curve. Now, what is happening, from 2D we did some simple operations like extrusion and rotation, rotational sweep. So, now what we did, we have started representing 3D objects in 2D form by just giving some small variations, that is translation sweep or rotational sweep. The geometric model produced, so you can see here, this is a topology, you say please extrude it in this direction, so you get a model. So, linear model and sweep extrusion was tried. The component sweep produced using translation sweep with taper in the sweeping direction is also possible. You can say this way. So, extruded solid with a taper. You can see here how did so this is a curve produced with linear sweep with the sweep direction along the curved surface. So, you can get, this is the sweep and then you said please sweep it in this direction. So, you try to get this. So, basically if you see, I define 2D and I get a 3D by doing some operational operations on the object. Component model producing using translation sweep with a overhanging edge. You can also try to make an overhanging edge. It is like opening of a lid. So, extruded solid with a hanging edge, we can also get that. So, 2D, if I could put it in a crude sense, it is 2D, 2.5D, then 3D. So, 2D to 3D you are making, and here in between translation sweep and rotation sweep you are giving. So, this I have already dealt. So, the rotation is done about an axis. So, these are various solid primitives which are available. If you wanted to understand little bit more, I will put it in such a way, such all these library functions are already available inside the CAD. And today all these things are available in the toolbox of even PowerPoint. So, all these surfaces are there. All you do is you define the diameter, you define the height, you get a cone. You define the cylinder diameter and then you say along the z direction you sweep or you extrude, you translate. So, then you get a cylinder. There is a predefined library function for the wedge. So, all you have to give is give the parameters, so you get an edge. Wedge to pyramid you can get, hemisphere you can get, cube or a block you can get, torus you can do, and then you can also get hemisphere. So, these are some of the solids. You see it is how interestingly moving, line, model, then you went to surface model, solid model. When you want, first what you could do 2D and now you wanted into 3D. So, first 2D, there were small variations like translation and sweep. Now, next stage what you have started doing is, you have started making standard primitives which are available, wherein which a program is written and stored. So, all you have to do is call that primitive and start giving this thing. So, you get a 3-dimensional object. See, look at the evolution how it happened in the CAD. And now with that evolution, people were little more smarter, they started adding the Boolean operation. So, what is a Boolean operation? You will have add, right, you will have union or you will have union or intersection, two Booleans. You will have union and you will have intersection. These two Boolean operations are now done. So, now what is the advantage? If you wanted to develop two different objects and these two different objects are to be connected, for example, I have a cup, and then I have to attach a handle. So, how do? I try to do B, A, and then what I get will be A union B. So, this is A union B operation. So, you see, after creating the simple models of 3D, people started using Boolean functions. These Boolean functions are used to develop 3D objects in a more creative manner. So, you can see here the Boolean operation and their effect on the model. You had a block, you had a cylinder. If you say subtract the cylinder from the block, you will try to get a side view will be like this object. If you wanted to join these two, then it will just form a single object. If you move the cylinder to the edge and then if you do an union, then it will become something like this. Become something like this. And now you say, I want only this portion to be taken or removed. So, then what do I do is I try to put the option of difference, I get the difference, and then I also try to say which is intersecting, get that portion alone I am able to get. Now, with this operations, you can try to make several primitives, do Boolean operations like union, difference or intersection, and develop different geometries. And the creation of a solid with 3D primitives in solid modeling, the constructive solid geometries. So, you can see here CSG is a constructive solid geometry. So, first what did you do? You used a block. So, in this block you union to one more block, you got this, and now you have put a cylinder, you have given the location for a cylinder, and then you said subtract the cylinder. So, subtract. So, you got this object. Then what you did? You created a slot and then you said please subtract it from the block, give a location. So, then this was generated, and then finally what you did? You started putting cylinders and this was put here, and then you start subtracting it from the solid. So, till now it is a solid. So, you see here solid, 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 and now what you did? You put two cylinders and put it there and said subtracted. So, now you see a complex geometry can be created through several simple geometries and by doing the Boolean operation. Constructive solid geometry follows this route, and again here it is also interesting to note, should I follow this route alone? Not necessary. These are the objects, these are the operations, you can do this as first and then you can start going next, whatever it is. So, there is not a unique representation of the union and subtraction, but ultimate object will be the same. So, till now what we saw was all about engineering surfaces, where it is all easy to draw, easy to manufacture. But what happens in real time or what is required in real time application is free form surfaces. So, free form surfaces to construct, you need to have more sophistication than whatever was existing till now. So, here again we will follow 2D, we will move to 3D. So, first we will talk about planar surfaces. In planar surfaces, it is a flat 2D surface. Then you have this we saw. Then next one is curved surface, single curved surface, that is a simple curved surface. Then double curved surface, which is complex surfaces generated not by a straight line but a curved object. Then ruled surface is a surface constructed by transitioning between two or more curves by using linear blending between each section of the curve. So, ruled surfaces, we will see what is ruled surfaces in the next coming slides. So, these are used for generating free form surfaces. Curve, single curve, double curve, then we went to ruled surface. Today you see in reality it is all free form surfaces. Model generated using sculptured surface, this is what is energy efficient, the drag is reduced, and then here if you see here no edge, no surface is straight flat, it is all curved, complex curves are there, and there is lot of other, inside a curve itself you have many variation facets. This is done by a CATIA software. When we talk about free form surfaces, in a nutshell, these are the various types of surfaces in the geometry. So, we will have planar surface, curved surface and free form surfaces. In planar surfaces, you will have planes. These planes are done by polygons and polyhedrals. When we talk about curves, there will be single curve, double curve. Cylinder, cone are part of single curve. Double curve is ellipse, ellipsoid, sphere, paraboloid and torus. These are all double curves. And then you will have ruled surfaces. From here it goes down to ruled surfaces. When we talk about freeform surfaces, you will have cone surface, you have B-spline, Bezier, NURBS and fractals. So, this is very important, and this is what is the big thing which CAD gave it to the manufacturing community. How do I generate freeform surfaces? So, by using cone surface. In cone surface we had B-spline, Bezier, NURBS and fractal. All the nature follows the fractal design. And finally, the lofted surface, ruled surface and lofted surface. This is an example for ruled surface. Ruled surface on the left is shown the curves from which the ruled surface on the right is formed. On the left is shown the curves, these are the curves from which the ruled surface on the right is formed. This is the right side formed. So, when we have two ruled surfaces formed between two space curves C1 and C2 with U as a control point or the vector. So, we will see C1, C2, okay, U and U, and now you see when we try to go in the other direction, you will try to get a surface like this, C1 and C2. So, two different ruled surfaces formed by two space curves C1 and C2. Both curves, all you have to do is the way you try to specify, you can try to generate two different surfaces. Next one, these are three different ruled surface: planar surface, cylindrical surface and conical surface. So, different ruled surface obtained from the same closed curve. The different surface results because of the difference in the selection of the start point on each side of the curve. So, just by changing the start point, you get different curves. Okay. So, ruled surface you will have three, which is planar surface, cylindrical surface and conical surface, and here just by changing the starting point, you see you will get three different types of curves or surfaces. So, different ruled surface obtained from the same closed curve. This is right and this is oblique. So, you can get any three different types of surfaces. It is different ruled surface obtained from the same closed curve, circle, cylindrical surface you can get, hyperboloid surface also you can get. So, we would stop here. We will continue in the next class. Thank you very much.